let's first remember that any object that's said to rotate outside of its own body, where the axis of rotation is far away compared to the size of the object, can be treated as a point particle. So when we say point particle, that's really a misnomer. What we're really talking about are objects that, if they're rotating, their point of rotation is far away, so that the extension of the object does not really contribute to the moment of inertia. That's what we mean when we talk about point particles. Now, this particular case that we're talking about isn't about its moment of inertia, but it is about its inertia. So we want to have the conversation where we have an object that's traveling in a straight line. So we'll say it's traveling along this line. And it has a velocity, say v, and a mass m. Now, we already know from prior experience that this object has momentum that is equivalent to the product of its mass and velocity. That this is a different way of measuring its inertia while moving. In fact, we've kind of developed a couple things related to this. One of them is conservation, and we use that when we deal with collisions, both inelastic and elastic collisions. We also know, and this is one that you guys tend to forget, but you need to not forget this, that the real definition of force is what it takes to change something's momentum. That's the real definition of force. In fact, the way Newton's second law should be written is as the rate of change of momentum. That's the way it should be written. We write it as ma, assuming that the object's mass stays the same. But the truth is, this is how it should be conceptualized, with the vector going over the direction of the change in momentum. This is another way of writing the impulse relationship, but it's something that is related directly to momentum and directly to Newton's second law. Now, when it comes to dealing with the angular momentum of a point particle, the thing I try to kind of indicate to you is that if you're standing here and you watch this object pass by, you'd have to rotate your line of sight in order to track this object as it passed you by. Does that make sense to you? In fact, if you were connected by a string to this object, as it passed by, it would cause you to turn. Does that also make sense? This is how we relate the angular momentum of a point particle as it travels in a straight line relative to some point in space. Now, this is a hard idea, but it's an easy implementation. But the first thing you have to note is that a single object has a different angular momentum depending on the observable point, or the point of rotation, or the point of reference. I don't know which phrase you'd like to use here, but every single different point of rotation would also produce a different angular momentum. Now, this is different than the way we classified linear momentum. Linear momentum was the same for all frames of reference. Angular momentum isn't. Angular momentum requires a point of rotation. Now, this wasn't any different than dealing with the rigid body angular momentum. The rigid body angular momentum had in it a fixed point of reference. That fixed point of reference is the moment of inertia. You chose a moment of inertia based on the axis of rotation for that object. So you were already doing this when you were dealing with the rotation or the spin of an object. And if you don't understand that, 'cause I'm looking and I'm seeing a little bit of confusion, consider if you have an object that's traveling in a straight line, every different point of reference is a different rotational axis. And therefore, that rotational axis would produce a different angular momentum, even for the same linear velocity. So when we talk about angular momentum, we want to choose a point of rotation that makes sense for the situation that is occurring. For example, say a disk that is spinning in space about a point through its center. It would have one moment of inertia. It would be 1/2 mr squared. But if I have that same disk, but instead of spinning it about the center, I'm spinning it about a point on the edge, then suddenly it has a different moment of inertia. I'd have to have 1/2 mr squared plus mr squared to shift the moment of inertia. So even if these two objects were spinning at the same omega, they would have different angular momentums because the point of reference is different. The axis of rotation isn't the same for each object. So when dealing with more common questions, and one of the ones we're going to start off with right out of the gate, looks something like this. There's usually some kind of bar that has a clear, fixed point of rotation, like right here. It's mounted so that it can swing about that point. Let's say that this is a top-down picture. So we're looking down on a surface where this is mounted at one point. And as we observe this object, we might have another object, a disk or something, that's traveling with some velocity towards this bar. Now, there's clearly going to be a collision. And regardless of what happens in that collision, it is very likely that the result of that collision will be the bar will begin to move. Wouldn't you agree? So if I wanted to deal with conservation of momentum, in this case, I'd probably have to look at angular momentum because the bar can only have angular momentum after the collision because it's fixed in place. Because of that, when I want to deal with the angular momentum of this particle, it would make perfect sense to make this point be the observable axis of rotation because it's common to both objects, and it makes sense since both objects are going to interact in such a way that their angular momentum will be conserved. It would not make any sense to choose this point over here as my observable axis of rotation. The bar can't rotate about that point. So even though I'm making kind of a big deal that a single object has lots of different angular momentums, for the sake of why we talk about angular momentum, there's only going to be one axis of rotation that matters. And it's going to be the one that is common to the interaction within your problem. So let's go back to dealing with just our single. We're going to see something like this. They're going to start the object over here and not tell you where it starts, but they're going to tell you the length of the bar. When you calculate the angular momentum, you're not going to have this distance or an angle. They're going to say some hockey puck is fired at your bar. You have to know that the angular momentum is going to be based on the length of this bar. Where it strikes the bar. Or if they move the puck, say, to who knows, they move the puck to here. And they give you this value, x, it's going to strike the bar right there. Okay, then its angular momentum is relative to x. That will be the point of closest approach to my pivot point. So, rather than use angular momentum as a calculation tactic, which I don't want to do, I want to use angular momentum in a sample question to give you an idea of how this is going to look so that you kind of get used to it. Because I'm never going to ask you a problem to say where I calculate the angular momentum of this random object flying through the air. That's just not necessary. We use angular momentum because it's a conserved quantity. And because it's a conserved quantity, it can predict the results of collisions. So we're going to do this problem that I have stationed right here. I'm going to redraw it with some specifics given to you. The first one we're going to do, I'm going to make it nice and straightforward and give you numbers. So that doesn't look like a bar very well. Let's try that again. So I have a bar, mass 2 kilograms. that is fixed in position so that I can rotate about this point at its end. So the mass of the bar is 2 kilograms. And let's say that the bar itself is 1.5 meters long. A piece of clay, which is tacky enough to stick to the bar, is fired at a velocity of 3 meters per second towards the end of the bar. Again, we are looking top down on a frictionless surface. If this blob of clay sticks to and attaches to the bar, what is the angular velocity of the system after the collision? Everybody hear the dynamics of the question? All right, let's say that the object has a mass of 1 kilogram, the piece of clay. Now, this is not the level of difficulty of your test. The level of difficulty of your test will be slightly greater than this, but this gets us a good start. There are a lot of pieces to this problem. I want to talk about every one of the little pieces that we have, but this is straight up a perfectly inelastic collision. It will have all the same rules that we had before, but we have to deal with angular momentum, not linear momentum. Now, in your notes, there's something big and bold you have to put in your notes. This collision does not conserve linear momentum. That should be in all caps and underlined. In order for linear momentum to be conserved, there can be no outside forces acting on the system. But this point right here applies an outside force to the system. It pushes on the bar to keep the bar from moving. So this system does not conserve linear momentum. It can be shown that the force on the bar does not cause a torque on the bar because the force acts at the pivot point. Therefore, there is no external torque on the system. That's why it conserves angular momentum. You guys do understand that those statements will be the reasons you have to give if you're asked to justify why linear momentum is or is not conserved. You understand the kind of question you're going to see, right? Check the box. Is linear momentum conserved? Why or why not? Is angular momentum conserved? Why or why not? If I was giving a test, that would be one of the last questions I'd ask to see if you truly understand it. So, let's work the problem now. Working the problem itself isn't all that big a deal, but I want to make sure that you've seen it done. So to work the problem, I want to remind you that these are usually best served by doing kind of a before and an after approach. This is how I like to look at them. There are two objects before and after the collision. Before the collision, there is the angular momentum of the puck and the angular momentum of the bar, which we know to be 0. It's not moving. Now, afterwards, there is just the angular momentum of the puck bar system. When that glob of clay attaches to the bar, they become one object. Now, in the past, we would just join the masses together. In this problem, we have to join the moments of inertia together. So let's see how this problem would look. First, I need to calculate the angular momentum, which is going to be R cross P for the glob of clay, plus 0 for the bar. Now again, we don't know where the glob of clay started, so we don't have that distance, we don't have that angle. We're not going to use either of those. We know that the angular momentum of that puck is the same, whether I deal with it being that far away or I deal with it right before it strikes. So right when it's here, that instant that it strikes, it will have the same angular momentum. So I will convert R cross P to R perpendicular times MV. Everybody follow along with that okay? I know it's hot in here, guys. I'm sorry. So, moving right along, we can actually compute the angular momentum with the information that's been given. R perpendicular is 1.5 meters. M is for the puck, it's 1 kilogram. And V is the velocity, 3 meters per second, which I wrote all of it out to make sure you see that the units come out correctly for angular momentum. 3 times 1.5 is 4.5. So this is 4.5 kilograms meters squared per second. That is the unit for angular momentum. Any question where I got any of that? Now, do you guys, I need you to be with me on this. You see where we're using that R perpendicular now and how we're going to use it. They're not usually going to give you these starting places. They're going to expect you to recognize that its angular momentum was staying the same throughout this path until right before it struck the bar. And they'll do that a lot, even in situations where it doesn't make sense. You're going to see one in just a minute. But let's go on, because there's more to this problem. Afterwards, we have a single object that now has the moment of inertia of the bar plus the moment of inertia of the clay. How am I going to treat the clay's moment of inertia? Point mass. That's right. It will be a point mass. It's rotating from some axis that is well outside the body of the object. So we'll treat it like a point mass. The bar, we'd have to look up. Something you'd probably be given on the exam. But a bar about its end is 1/3 ml squared. So 1/3 ml squared. That's the moment of inertia of the bar. The clay is just mr squared, where m is the mass of the clay and r is the length of the bar, because it's stuck at its end. That's now the moment of inertia of the system. This omega is going to be the angular speed of the system after the collision. This whole thing's going to rotate that way. Now, I know you guys can run a number on this. I'm not worried about you guys running numbers. But you guys work the numbers. But the numbers aren't that important. So can you guys maybe think about doing that in a little bit and consider a few other things I'm going to say here. What are some possible after questions here? Where do you think a person like me would go if I was going to start asking you further follow-up questions? Yeah.
How high does the bar go?
Yeah, if this was instead not looking down on like an air track, but the bar was hung and I struck this from the side, yeah, I could ask you questions about how hard the whole thing swings upwards, right? The maximum displacement. I could run the reverse to that. I could tell you what angle it swings upward and then ask you how fast the clay was going. I would also probably ask you how much energy was lost during the collision. The puck had all translational kinetic energy, 1/2 mv squared. Afterwards, our system had rotational kinetic energy. I guarantee the energy was lost. I could ask with how much force the bar has to exert on the clay to keep it from flying off. There's a centripetal force on the clay. Without that force, the clay doesn't stick. And make you figure that out. Do you see all the different applications that can be here? I mean, you guys have done optimization now. There's absolutely no reason not to ask you where is the most optimum place to strike the bar to maximize the velocity. It might not be the end of the bar. I mean, if you think about baseball, where's the sweet spot of the bat? It's not at its end. So there are a lot of follow-ups here, a lot of places to go. But do you see this as a basic problem? Any questions about this as a basic question? Yes, sir.
When you say from like top down, like, what do you mean by that?
I mean, this bar was horizontally on your table, and the puck was just rolled to the side of it. Okay, that's looking top down on a situation. Does that make sense? So if you hear the word air track in your problem, they're talking about like an air hockey table, and you laid the bar on there. Now, I want you to think about this for just a moment. What if the object had not been pinned in place? The level of difficulty of the problem goes up dramatically. Okay, I want to be very clear about it. So this problem is nice because although it seems complicated, it is relatively constrained. We know the direction that things will move after and before. But the moment I pull that pin out and redo this problem, where's the point of axis? Where's the point of rotation now? It would likely rotate about its mutual center of mass between the bar and the blob of clay, which will be probably here someplace. It also probably won't go in a straight line. It'll probably have some rotation afterwards. So be aware, the problem's level of difficulty on this example is actually relatively low compared to the potential location we can go. 2 years ago, they asked a question about a floating round chunk of ice or a platform that was on ice. And a kid ran and jumped on the platform. It was not fixed in space. The whole thing could spin after the kid jumped on it. It was tough. You're not going to see it as a test question. You are going to see it as an in-class FRQ for us to explore because it was a tough question. Now, I'm going to hit pause for an object and a single point of rotation because this is where we have to get to the particulars of the mathematics. Now, when I'm drawing this, I want to draw this line that represents the path the particle is going to travel on. And I'm trying to make sure that it anticipates future positions where the object will be. So the object is traveling along that line with a velocity v and mass m. Now, in order to calculate the angular momentum of this particle, and this part's going to be a little bizarre to you in the beginning, but it works out and it's kind of fascinating. The angular momentum, which we use a lowercase l for the angular momentum of a point particle, it is a vector like any momentum is, and it is a cross product. It is the cross product of r cross p. So it involves the linear momentum of the object and a value r, which represents the torque arm length. Now, that part's going to be a little weird. But R represents that vector. That's R. Yeah?
Does the cross, like, you know how they have the line on them saying direction matters? Is that what the cross product does? Or do we still have to, like, take it into account in a different way?
No, you still take account in a different way. The cross product is a way of multiplying vectors. So both R and P are both vectors. So that suggests that the angle between them is going to matter in some way. Now, this cross product produces a vector quantity, the angular momentum, which has to be in agreement with the other ways in which we've done cross products with the right-hand rule. So let's start by considering that the angular momentum will have a direction, a rotational direction that's either into the board or out of the board. depending on how we work the cross product. Now, if you don't remember how to do a cross product in this instance, remember, it's your three-finger rule will work the best, with the pointer finger being the first vector and the middle finger being the momentum. So when I look at this, the cross product will be r towards the mass from the point. That's r. Your middle finger, you have to try and arrange to be in the direction of the momentum, which will be along the velocity. And your thumb will point in the direction of the angular momentum, which means that I see a cross product that is into the board. Do you guys see that? Now remember, it has to be in agreement with what we said about angular momentum. This line, if we say that this line is going to connect this mass to that point all the time, then how is that line sweeping out angle? Is it not sweeping in this direction to rotate like this into the board? It has to be in agreement. So if we look at where this mass is going to be in a few moments, the mass is going to be, say, over here after a while. When it's over there, it's going to have the same linear speed. But now, that vector for r lies in that direction. If we were looking at the angular momentum of the particle and its direction is about this point. It would be into the board. It's sweeping out angles just like we would expect. So r cross p is how you calculate the angular momentum, which means that the magnitude of the angular momentum is r times p times the sine of the angle between them, where this represents the angle between them. Patience. The thing you have to be aware of is this suggests that there's a different angular momentum everywhere. And if you're looking at that, I mean, you have an angle over here. This r has now changed. It's shorter. This angle has changed. In fact, it seems as though no matter where the object is, oops, that's not what I want to draw. No matter where the object is, it might have a different angular momentum. It will please you to know that that is not true. And we're going to prove that. I want you to consider that if each of these has the same velocity, same size vector velocity, but we're looking at three different cases of where the object is. Are we following that so far? We're looking at three different cases for where the object is. Now, I don't need to prove it for three cases. I really only have to do it for one, but I want to be as complete as possible. I want to show you that no matter where this object is, its angular momentum is actually the same at all of these points, even though r and phi are both changing. Let's consider what this actually tells us right now. Okay? So I want to draw in some things for that, but I want to focus just on space 1. So the angular momentum at location 1. Okay? Now, if you'll notice, r sine phi is in here. I want to group that together and put the momentum away from it for just a minute. So we're looking just at r sine phi. Now, r represents this length right here. But when I multiply it times the sine of phi, I'm actually creating a right triangle that lives right there. Right? If this were r and this were the opposite side, wouldn't sine phi equal O over R for that triangle? You guys see that okay? So what we've done in making that calculation is R sine phi actually represents that distance, the perpendicular distance, or the point of closest approach. Now leave that in the back of your mind for a minute. Let's get rid of all of that. And let's focus on position 2 instead. Okay? If I focus on position 2, suddenly that is my R. This is my phi. But do you notice even still that R sine phi defines this triangle, where this is the opposite side again? Do you guys notice that? Suggesting that R sine phi is still creating for us this same distance, this same point of closest approach. Now, let's go to my third case. So we're looking at R3 right here. It defines this triangle. Unfortunately, we have this angle, which is clearly greater than 90 degrees. But we know that this angle will produce the exact same value for sine, right? The sine of the supplement produces the same answer. Do you all know that already? Okay. Sine is positive in both the first and second quadrant, which means that the sine of, say, 60 is the same as the sine of 120. They're just on opposite sides of the y-axis, and they're both positive. So you can say that the sine of phi is equal to the sine of 180 minus phi. That's why we get the same value for this length. You should prove it to yourself if you don't believe me. But it will work. Now, that being said, do you realize that the reason r sine theta works is it's always pointing to the same place? Let me get rid of all this green I've written in here. That in all of these cases, the actual angular momentum could be written as r perpendicular times the momentum. I mean, if you could drop a straight perpendicular to here, this is r perpendicular, then no matter where the object is along that line, its value for its angular momentum is based on this point of closest approach. That's why it works. It's part of the reason it works, at least. What's really, really interesting about all of that is that that's how they're going to do every one of the problems. Every single problem. There's been a number of ways in which these problems have been asked. This is one of them. This was years ago, had a spoked wheel or a spoked disc. I can't remember exactly what it was. That's probably the worst looking spoked wheel ever, but you'll forgive me. And they fired a dart at it, so the dart stuck at the top of the wheel, and then asked what the rotational speed of the wheel was. You do see it, that's the exact same question we just did, right? That you would not have to change very much. You would need to know, the radius of the wheel. It was fixed at its center, so they gave the size of the wheel, they gave the number of spokes, they said it was a ring, they told you how fast the dart was fired, they gave the mass of the dart, stuff like that. Then they changed the problem immediately and had the dart strike some random place on the side of the wheel. That did make it harder, because now you don't have a simple, straightforward value for r. R became that value, right? It struck actually at an angle relative to the radius. So there are ways that the problem can be changed and add certain amounts of subtlety to it. Do you realize that there would be no exchange in momentum if it struck right along a radius pointed at the center? that it would not cause the wheel to rotate. So these are slight variations. These problems have been asked throughout the years, but this is how we deal with the angular momentum of a point particle. All right, questions about that? Yeah.
For this one, for like the moment of inertia, would you have to take into consideration all of these spokes? And then
The particular problem they gave us a value to use for the moment of inertia of the object. They just said that I equaled some number. So in that year, you did not. There was a year where they had a spoked wheel, and you had to come up with the moment of inertia of a combined object with 6 spokes. It wasn't hard. It was, 6, I think it was 6 times 1/12 ml squared for the spokes, where L had to be 2 times the radius. And then you had to add that to mr squared for the ring that represented the wheel. But yeah, that kind of problem is considered to be a perturbation, a wrinkle added to a problem to make it slightly more complicated, to see if you catch on to the fact that the object is a combined object. In the same way that a couple of years ago they had a 4-wheeled cart, where every wheel was a disc, which had its own moment of inertia. You had to add up all 4 of those, then add it to the mass of the cart, but then it had a rotational inertia that was just the wheels. Yes, they have those things. All right.